Hello friends, I am Shivaji Soloni. Welcome to the class of physics. In this video, I revise the concept of oscillation. First concept of the oscillation is linear and this linear simple harmonic motion. Consider the example of spring and block. The spring is attached to the rigid support and to the other end one block which is at the mean position. So at the mean position there is no any force acting and the compression of the spring, the force is acting on the block and this force is always directed towards the mean position. So some conditions for this linear simple harmonic motion. So this motion is along the straight line and the net force acting on the block at the mean position is equal to 0. This is the equilibrium position. And the force acting on this block is directly proportional to the x. So to understand the definition of linear simple harmonic motion here, the linear simple harmonic motion is defined as the linear periodic motion, means the motion which repeats itself after equal interval of time. Motion of the body in which the restoring force is always directed towards the mean position and the magnitude of the force is directly proportional to the displacement from the mean position. So according to these two condition definition, the force is proportional to the displacement and this proportionality constant is equal to k and this k is known as force constant. This negative sign indicates that the direction of displacement and the direction of force is exactly in opposite direction. So F is equal to minus kx. So we get the equation of force constant k is equal to F upon x. So unit of force constant is Newton per meter and it defined as the restoring force per unit displacement. So we get the dimension of this force constant m1, L0 and t minus 2. Next one, differential equation of linear simple harmonic motion. To derive the differential equation, this first equation according to the concept of linear simple harmonic motion. Second equation, F is equal to mass into acceleration. This is according to the Newton's second law of motion. So in the second equation, write down the acceleration. This acceleration is a dv by dt, rate of change of velocity with respect to time. So put the value of velocity dx by dt. Simplify it, we get this acceleration is equal to d2x upon dt square. Then the equation of force F is equal to m d2x upon dt square. Put the value of this force in the equation of linear simple harmonic motion. Simplify it, m d2x upon dt square is equal to minus change divided by m to the both sides. So we get the equation d2x upon dt square plus k upon mx is equal to 0 and this equation is known as a differential equation of linear simple harmonic motion. Put the value of k upon m is the omega square. This omega square is the angular, this omega is the angular frequency. So k upon m is the positive quantity, omega square is the positive. So this omega may be positive or the negative because it is the angular frequency. So according to the differential equation, we can derive the expression for acceleration, velocity and displacement. So first one, differential equation for linear simple harmonic motion, simplify it. To the left hand side there is the acceleration. So equation of acceleration is equal to minus omega square x. Negative sign indicate that acceleration and displacement are in opposite direction. So next one, we just calculate the minimum and maximum value of acceleration. Minimum value, so at the mean position, two cases are there, at the mean position and the extreme position. At mean position, x is equal to 0 and at extreme position, x is equal to a, that is the amplitude, maximum displacement of the body from its mean position. So we get the acceleration is minimum at the mean position, which is equal to 0 and acceleration is maximum at the extreme position. So this is the condition at the two extreme points and this is the mean point. X is equal to minus a, x is equal to plus a. So at the mean position the value of acceleration is equal to 0 and at two extreme position value of acceleration is plus or minus a omega square. Next one, expression for the velocity in linear simple harmonic motion. Acceleration equation dv by dt Modify this equation in terms of x, dv by dx into dx by dt. Dx cancel, it is remains same. So it is dx by dt is equal to v. So put the value of acceleration. It is equal to minus omega square x. Simplify it, we get v into dv. So separate the term, x term to the one side and v term to the other side. Integrate this equation on both the sides. We get integration of v into dv, it is v square by 2, and integration of x dx is x minus x square by 2. Minus sign is as it is. Simplify it, find out the value of this integration constant c, put the condition of this equilibrium condition, that is at extreme points x is equal to plus or minus a, velocity is equal to 0. So we get c is equal to omega square a square upon 2. Put the value of c in this equation of velocity. Simplify it, 2 get cancelled, so we get the equation of v square is equal to omega square in bracket a square minus x square. Modify this equation. Finally, the equation of velocity v is equal to plus or minus omega under root a square minus x square. Omega, or this is plus minus velocity. A, capital A is the amplitude, x is the displacement, omega is the angular velocity, and this is the instantaneous velocity or linear velocity of simple harmonic motion. Then calculate the maximum and minimum velocity at the mean position and extreme position. Velocity is maximum at the mean position and it is minimum at the extreme position. This is the case at the two extreme cases and the mean position with respect to the acceleration and velocity. Acceleration, so it is exactly opposite. Acceleration is maximum at extreme position, but velocity is minimum at extreme position. Acceleration is minimum at the mean position and velocity is maximum, that is a omega. Calculate the expression for displacement. So use the equation of velocity v is equal to omega under root a square minus x square. Put the value of v dx by dt. Then separate the terms of dx and separate the terms of dt and integrate this equation. So when you integrate this equation on both the sides, we get the integration according to the formula of integration, that is sin inverse x upon a is equal to omega t plus alpha. Finally simplify it, the final equation, x is equal to a sin of omega t plus alpha. So this is the expression of displacement of the particle performing simple linear simple harmonic motion. Calculate its value at mean and extreme position. At a mean position, x is equal to 0, t is equal to 0. So value of this phase alpha is equal to 0. So x is equal to a sine of omega t. This is the displacement at mean position. At the extreme position, x is equal to plus or minus a. So put the value of x is equal to plus or minus a. We get the value of alpha is equal to pi by 2. Finally, the displacement equation at the extreme position, x is equal to a cos of omega t. Next concept, that is the derivation of simple harmonic motion when the particle or it is in the uniform circular motion. Simple harmonic motion as a projection of uniform circular motion. When any particle in uniform circular motion, then the line joining between the particle and the point M moves along the two extreme points of the diameter, that is between A and B in the uniform circular motion of the particle. So according to this diagram, we just calculate the value of this angle O after time t is omega t plus alpha. So we get, simplify it according to the triangle OMP. OMP, right angle triangle, write down this sine omega t plus alpha value, and it is exactly equal to OM upon OP. OM is equal to x upon a. So we can write down this value is same as this opposite angle. So x is equal to a sine of omega t plus alpha. Expression of displacement in case of projection of uniform circular motion. Integrate this equation with respect to time, we get the velocity equation. Similarly, equation of this velocity, integrate this just differentiate this equation with respect to time, we get the equation of acceleration also. So acceleration is equal to minus omega square x, and this equation is same as the last three equations. Equation of displacement, velocity, and the acceleration. Next one, that is the energy in uniform circular, energy in linear simple harmonic motion. We get the two equations, that is the equation of potential energy and equation of kinetic energy. Potential energy is equal to 1 half kx square and kinetic energy is equal to 1 half m omega square in the bracket a square minus x square. This is the expression for kinetic energy. And when this kinetic energy and potential energy is combined, the total energy in uniform circular motion, this linear simple harmonic motion, remains constant, and it is 1 half k a square. There is the amplitude square. So according to this graph, we can conclude that at the extreme position, this potential energy is maximum and the kinetic energy is minimum, and at the mean position kinetic energy is maximum and the potential energy is minimum, but the total energy is remains constant. Next one, expression for time and the frequency. Periodic time means the required time to complete one complete oscillation is known as periodic time. So put the value of omega, it is k upon m under root. So T is equal to 2 pi under root m upon k. M is the mass, k is the force constant. So calculate the equation of frequency also. So we get m by k. Just calculate this periodic time in terms of acceleration. So what is omega square? It is f upon mx. So omega square is equal to a upon x. Omega is equal to a upon x. It is acceleration per displacement. So put the value of omega in this last equation. We get the periodic times in terms of acceleration per unit displacement. So T is equal to 2 pi under root a upon x. This is also expression of period. Same thing, calculate the frequency. Frequency means number of oscillation completed per unit time by the particle in the simple harmonic motion is known as frequency. So reciprocal of the periodic time is also known as frequency. Just take the reciprocal. We get f is equal to 1 upon 2 pi under root k upon m. Graphical, next point, graphical representation of simple harmonic motion. There are two cases when the motion start from the mean position, and second case when the motion start from the extreme position. At the mean position, alpha is equal to 0. At the extreme position, alpha is equal to pi by 2. So at mean position, alpha is equal to 0. So we get x is equal to a sine of omega t. Differentiate it. Velocity v is equal to a omega cos of omega t. Again differentiate it, we get the equation of acceleration. So acceleration is equal to minus a omega square sine omega t. So these are the three equations: displacement, velocity, and acceleration. When you plot this by using the data table with respect to time or with respect to the phase value, angle value, put the value of this omega t in the equation 0, pi by 2, pi, 3 pi by 2, 2 pi, we get the value of displacement. So this is a displacement graph with respect to time, start from the origin, and it is maximum at, this is t by 4, means at the pi by 2. So this is the sine function. Similarly, draw the graphical representation for the velocity. Velocity is the maximum at the mean position, so it is the cosine graph, start from the maximum value. Similarly, calculate the value of acceleration and plot the graph of acceleration. This is also sine function, but the first loop is the negative loop. So we can conclude The graphical representation of linear simple harmonic motion in which it is start from the mean position means the displacement and acceleration is the sine function. There is a phase change of pi, then the displacement and velocity both are sine and cosine function, and the phase change is equal to pi by 2. Both the this displacement, velocity and acceleration, that is linear simple harmonic motion, is periodic in space and periodic in time. So this is the some conclusion part. Next one, motion. One example of this linear simple harmonic motion, that is the motion of simple pendulum as a simple harmonic motion. Simple pendulum means one metal sphere is there attached to the string to the rigid support. Angle is equal to theta. So the tension acting on the string is get split into the two component mg cos of theta and mg sin of theta along the tension and perpendicular to the tension. Then the restoring force, the resulting force for the linear simple harmonic motion is minus mg sine of theta. Whatever the oscillation of the simple pendulum is due to this restoring force. So we get F is equal to minus mg theta because theta value is very small. So theta is equal to, it is arc upon length. What is the arc value? X upon length means L. L is the length of the string. So theta is equal to x by L. Put the value of theta in this last equation, we get minus mg x upon L. So F is equal to minus mg upon L into x. From this equation, calculate the periodic time, because periodic time it is, so this is the force equation, A equation, we get A is equal to minus g upon L into x. So finally the equation of periodic time for the simple pendulum is capital T is equal to 2 pi under root L upon G. L is the length of the string and G is the gravity. Reciprocal of period is the frequency. Different laws according to the last equation, it is periodic time is directly proportional to the square root of length. Law of acceleration, it is inversely proportional to the square root of gravitational acceleration. Law of mass, period of simple pendulum is independent on the mass of the this sphere or the block which is attached to the string, and the period of simple pendulum is independent of its amplitude when it is very small. Seconds pendulum, the simple pendulum whose time period is 2 seconds is called as seconds pendulum. So put the value of capital T is 2 seconds. Simplify it, length of the seconds pendulum is g upon pi square. Differential equation of damped harmonic motion. What is damped harmonic motion? Means the motion in which its amplitude is decreases with respect to time. So there are two factors which affect on the motion. One is the damping force and second one is the restoring force. Damping force is directly proportional to the velocity. So this F is equal to minus BV, and this is the restoring force, F is equal to minus kx. So total force is equal to Fd plus Fx. Fs, that is the, this is the restoring force. Put the value, we get the differential equation for damp oscillation. So this is the solution of this differential equation, and according to this solution or according to this concept, we can conclude that this damping force or damp oscillation is the exponential motion, or you can say that in this case the amplitude of this oscillation is exponentially get decreases. So this is the some expression in the damp harmonic oscillation. Undamp means, what is meant by undamp? The amplitude of oscillation is remains constant. So this is the part of the oscillation concept.